Alright, let's explore this idea of an edge trigger device built out of cells, and I'm going to use the same circuit that's described in the lecture slides on edge trigger devices, but I'm going to simulate it using the Java-based simulator. So I'm going to invoke that with JavaSim, and I recommend looking at the lecture on tool usage to understand better what's going on in here. But basically I'm just going to use the command line of this simulator to compile these cells to implement a D flip-flop. The clock will come in from the north, the D input from the south, and we'll just explore how it looks by interacting with it. In this simulator I can change inputs from a 0 to a 1 by just clicking on the arrow going into cell's picture. So if I click on this, the input will change to a 1, and you notice I turn from a thin line to a thick one. If I click on it again, it goes back to a 0. So I'm going to compile the definitions for these three cells. The cell on the west, remember, just recirculates from the east to the east. So I'm going to say compile cell 0, 0. I'm going to say data east equals east. That's the only equation. And then I'll end my cell definition with a period. And you notice the cell changes from gray to blue, indicating there's something in there. If I point at it, I can see the equation on top, data east equals east. Or I can click on it and see the equation over here. Incidentally, I can also say dump 0, 0 and see the truth table, or I can say boolean 0, 0 and see it written out as an equation. Now I'm going to compile the middle cell. This is the one where all the action happens. So I'm going to say compile 0, 1, and I need two equations here. For the data east, I want that to be equal to the AND of east and north, or the AND of west and north bar. So west, north bar, and then OR those. And you'll notice I'm writing in reverse Polish notation. That's how all the truth tables are input in this tool. So there's the data east value, and the data west value is equal to south north or west north bar. We AND those and then we OR them together. So straight sum of products representation, put in a period to end that definition, and now we've got our middle cell defined. Now I'm going to compile cell 0, 2, and that's just going to recirculate from the west back to the west, and also copy from the west out to the east. A couple of things to notice here. One, the way these cells are defined, we put the inputs on the right and the outputs on the right. The output needs to say whether we're doing a control output or a data output, so we say data east, data west. But on the right hand side where we're specifying inputs, all our inputs are always D's, so we can just use compass directions. Also, if you don't like reading reverse Polish notation, we can say, for example, boolean 0, 1, and see the equations for this middle cell in a more standard form. East and north or west and north bar, for example. And data west to south and west, south north or west north bar. So now if I tick the clock, nothing happens. Our output from the flip-flop should be coming here, and it's a 0 and it remains a 0, because the D input, which is coming from the south here, is simply stuck at 0. So we need a way to access this. We can't click on this arrow because it's internal to the matrix. We can only affect edge cells. So I'm going to compile a program into this cell, cell 1, 0, as follows. I'm going to say compile 1, 0, and I'm just going to say data east equals west. So whatever data comes in from the west now gets passed to the east. The last thing I have to do is compile this cell to take data from the west and send it to the north. That will give me access to the D input of this middle cell on the flip-flop. So I'm going to say compile 1, 1, data north equals west. And now when I click on this edge cell, my 1 gets transferred into the southern input of this middle cell of the flip-flop. And now I can put in a 0 or a 1. And I can begin to explore this flip-flop's behavior. So clicking on this cell has no effect, seemingly. But if I set the input on the D side to a 1 and I click the clock goes high, and you can see this bit is being trapped over here. The output has not changed yet. But when I drop the clock, the D value will appear on the output. And now I can change the output, the D input, and the output doesn't change. It's totally stable. If D stays high and I tick the clock again, nothing changes. The output is still 1. But now if I drop the D input and I tick the clock, you can see the 0 is loaded in the slave side here, and when the clock drops, it propagates through to the output of the flip-flop. So it's acting like an edge trigger device, and that's very useful. And this is the same kind of approach that you would use for building a JK flip-flop or a toggle flip-flop to make counters and so on. So that's just a graphical simulation of the design of an edge trigger D-type flip-flop.